We are in Chapter 1, Section 1, where we discuss the background to mechanics of materials. This is Session 1, and we give an introduction, discuss action-reaction pairs, and start our treatment of plane trusses. One would be curious as to why we discuss action-reaction pairs, since it is normally not done. We believe that understanding action-reaction pairs will help us with plane trusses and plane frames. It will also help us deal with other topics in mechanics of materials as we go forward. This is a block diagram with the sessions covered in the first 4 chapters. There are 36 sessions overall. Hence, this is a road map that we will traverse. We are starting now, so we are in session 1. Here in section 1, we'll discuss the background, which we think will help us as we go forward understanding mechanics of materials. In order to understand action-reaction forces, free body diagram, and equilibrium, we'll look at Newton's third law. We'll also look at plane trusses and plane frames. As per Newton's third law, single force is an impossibility. Forces always operate in pairs. There's an action force and a reaction force. If you want to draw the free body diagram of a given body, then we look at the forces that the environment exerts on the body, not the forces that the body exerts on the environment. Once we have the free body diagram, we can look at equilibrium. Now, plane trusses are a coplanar system of pin-jointed bars forming a rigid structure. The forces in plane trusses act along the axis of the members. They are either tension or compression. We can analyze plane trusses using the method of joints, where we look at the equilibrium of the joints of the truss, and from that we find out the forces in the members. Plane frames are also coplanar system of pin-jointed bars forming a rigid structure. But unlike plane trusses, transverse force can act in between the ends of the members. Members are subjected to not only to tension and compression but also to bending. To analyze plane frames, we look at the equilibrium of each individual member. Forces in the members are generally not aligned with the axis of the members. Trusses are also analyzed using the method of sections. So if the whole truss is in equilibrium, then a portion of the truss will also be in equilibrium. We consider the equilibrium of a portion of the truss and find out the forces in the members of the truss. The method of sections is quite important since we will use it in other chapters. So here we have very briefly discussed the issues that we will cover in this section. We believe that as we go forward, this understanding will help us with other chapters of mechanics of materials. Here we discuss action-reaction forces, free body diagrams, and equilibrium. And for that, we refer to Newton's third law of motion. Newton's third law of motion is given by the common phrase, for every action there's an equal and opposite reaction. Here we'll look at two examples and consider action-reaction forces. So this is the first example of a hand pulling a rope attached to a block. We consider that the coefficient of static friction between the block and the surface is quite high, and the hand is pulling the rope with a small force. Hence, the block does not move. There are three sets of action-reaction forces here. The first is between the block and the surface, which we won't discuss any further. We discuss the other two action-reaction pairs as shown. So here the hand is pulling the rope with the force Fh, and the rope is pulling the hand with the force Fr1. The rope is pulling the block with the force Fr2, and the block is pulling the rope with the force Fm. Vectorially, we can say that Fh is equal to minus Fr1 and Fm is equal to minus Fr2. Even if the rope has a mass, since there's no acceleration, these forces will be equal in magnitude. So based on Newton's law, we can say a single isolated force is an impossibility. Two forces are involved in interaction between two bodies and are called action force and reaction force. They are equal in magnitude, opposite in direction, and lie along the line joining the two bodies. It is to be noted that the force acts on different bodies. We now consider a second example. This is a block suspended using a spring from a ceiling. There are four action-reaction pairs involved here. So the spring is pulling the ceiling, and the ceiling is pulling the spring. This block is being pulled by the earth, and the block is pulling the earth. The spring is pulling the block, and the block is pulling the spring. Also, the spring is pulling the earth, and the earth is pulling the spring. Let us now look at the equilibrium of the block. The block is being pulled by the spring, and also the block is being pulled by the earth. Since the block is in equilibrium, the vector sum of the forces acting on the block add up to 0. So T plus W add up to 0. Here we haven't discussed the forces that the block itself exerts on the environment. Let us now look at the equilibrium of the spring. The ceiling exerts a force on the spring. The block exerts a force on the spring, and the earth exerts a force on the spring. The spring is in equilibrium, so P plus T dash plus W is equal to 0. That is, the vectorial sum of forces is equal to 0. Again, notice that we have not considered the forces that the spring exerts on the environment. Here T is the force that the spring exerts on the block, and T dash is the force that the block exerts on the spring. So P and P dash form an action reaction here. Similarly, if the spring exerts a force P dash on the ceiling, then P dash and P form an action reaction pair. One would be curious about the action reaction force between the block and the earth. We are familiar with the gravitational force that the earth exerts on the block. However, the block also exerts a force on the earth. Since the earth is huge, the acceleration is very small. Here we discuss the free body diagram. We give two examples. The free body diagram can be drawn directly, or if we have an arrangement of bodies, we can look at the action-reaction forces of the bodies, and we can look at a particular body and draw the free body diagram. Draw the free body diagram, we first need to identify that body. Then we need to look at all the forces that the environment exerts on the body. We need to fix a reference frame so that our job becomes easier, and that is resolution of forces becomes easier. We next need to draw the body, the reference frame, and all the forces that act on the body. We leave out all the forces that the body itself exerts on the environment. So here we consider the case of a block in a smooth inclined plane held by a string. The plane is considered smooth because in that way there are no forces along the plane. So the block is acted upon by gravity, so there's a force pulling it downwards, and it is acted by the string, so the string is pulling it, and also there's a normal force due to the inclined plane. The block itself exerts opposite forces, so it pulls the earth, and there's a reaction force on the string, and also there's a force with the inclined plane. There's another action-reaction set here, that of the string pulling the wall and the wall pulling the string. Reference frame here is so selected with the x-axis and the y-axis, so that resolution of force becomes easier. The weight mg acts downwards as shown, and in this diagram, as we see, all the forces that act on the block are shown. Resolution of forces being easy, the magnitude of force F1 would be mg cos theta. The magnitude of force F2 would be mg sin theta. Here we consider a second example. So we look at action-reaction forces, the free body diagram, and equilibrium. So this is a case of a mass suspended by three strings. Initially, we'll look at the action-reaction forces. So the ceiling is pulling AB, and AB is pulling the ceiling. The ceiling is pulling AC, and AC is also pulling the ceiling. The mass here is being pulled by the earth. The mass itself is pulling the earth. AD is pulling the mass, and the mass is pulling AD. Now the knot at A is being pulled by AC, AB, and AD. and the knot itself is pulling these three strings. We consider the equilibrium of the knot. So the knot is being pulled by FAB, FAC, and FAD. So these are not the forces that the knot itself exerts, but the strings exert on the knot. The knot is in equilibrium, so the vector sum of forces acting on the knot would be 0. So FAB, AC, and AD add up to 0. This is a vector equation, and there's no forces in the z direction. So the scalar equation would be FABX, FAC, x is 0, and FABY, ACY, and ADY would add up to 0. Or we can say FAB cos 30 minus AC, FAB cos 30 minus FAC cos 60 is equal to 0, and FAB sin 30 and FAC vertically would be equal to W. If the weight W is 500 newtons, then you can use these two equations to find FAC and FAB. So FAC turns out to be 433 Newton and FAB 249.9 Newton. Where we start discussing plane trusses. Plane trusses are a system of bars that lie in one plane and form a rigid structure. The forces in the plane trusses act along the axis of the members. So they may be tension or compression acting along the axis. The bars are considered weightless. The hinges can be pinned, can be welded, or can be riveted. We consider that the hinges are frictionless, or they are idealized as frictionless, and the forces are applied on the hinges. The plane of the force is also same as the plane of the truss. Here we have taken two types of common support shown as A and B. A is a hinged support, and it can withstand loads both in the vertical direction and the horizontal direction. B is a roller support, and it can withstand forces only in the vertical direction. In this particular case, B is also vertical, and B can withstand only force in the vertical direction. Then the force in A will also be in the vertical direction. The truss on the whole is in equilibrium, and each of the bars in the truss are also in equilibrium, and each of the hinges are also in equilibrium. The reactions of the bars of the truss are equal and opposite to those exerted by the joints. The common line of action is the axis of the bars. We deal with trusses that are stable and also trusses that are determinate. So they can be solved using the equation of statics. So with the plane trusses, we'll first take the truss as a whole, consider the truss as a whole, and find out the reactions, and then we start looking at the joints. Trusses are made of bars that are pinned at ends and subjected to axial forces. So we'll study here the case of a bar subjected to a axial force. and pinned at both ends. We'll look at the equilibrium of the pin at A and B and the equilibrium of the bar AB, and then we will look at the action-reaction forces that act at A and B. So at A, the pin A is being pulled by the bar AB, and it is also being pulled upwards by the bracket. At B, the pin is being pulled by the force P, and it is also being pulled by the bar AB. The bar AB is being pulled by the pin at A and the pin at B. So in the cases of figure 3 and 4, the forces are the forces that act on the pins, not the forces that the pins exert on the environment. Here also in bar AB, we only deal with the forces that act on the bar due to the pin, not the forces that the bar exerts. Looking at the action-reaction sets, there are two action-reaction sets at A. The bar AB pulls the pin downwards, and the pin reacts with an upward force. The bracket pulls the pin upwards, and the pin reacts with a downward force. Here at B, the force P pulls the pin downward, pin reacts with an upward force. AB pulls the pin upward, and the pin reacts with a downward force. We can now look at two action-reaction sets. The pin at A is being pulled by AB. If this force, let this force be M, then the bar at AB is being pulled by the pin, and so let this force be M dash. So these two form an action-reaction pairs. They are forces acting on different bodies. Here the force is acting on the pin, here the force is acting on the bar. Similarly here, the force N is acting on the bar, and here the force N dash is acting on the pin. So N and N dash form an action-reaction pair. Here we consider the method of joints. There are two methods to find forces in a plane truss. That is the method of joints and the method of sections. So let us take a plane truss. The plane truss shown here, it is acted by a force P. Initially, we take the equilibrium of the whole truss, and we find out the four external forces acting on the truss. That is, in this case, the reaction at B and the reaction at A. Once we have found out the reaction that are acting on the whole truss, we consider each of the joints. Now, if the whole truss is in equilibrium, each of the joints are also in equilibrium. We earlier discussed the case of a weight hung by three strings, and we took the free body diagram of the knot that connects the three strings, and in that way we found out the forces in the strings. So in the similar manner, we can take the joints and considering its equilibrium, we can find the forces in the members. The equation used to find out the forces in the joints our summation Fx is equal to 0 and summation Fy is equal to 0. Just as the joints are in equilibrium, each of the members such as AC or CD are also in equilibrium. It can be shown that if the forces act on the pins and the structure is made of bars connected by the pins, then such a structure would be subject to only axial forces. This is the same truss as we considered in the earlier slide. Here we are given the angle at A, B, and B. We'll first look at the geometry of this truss, then we'll consider the equilibrium of the whole truss and find out the external reactions. And finally, we'll look at equilibrium of joints such as the joint at A. The angle at A and B are both 30 degrees. So the triangle ACB is an isosceles triangle. The angle at A is 30 and the angle at D is 60. So the angle ACD is a right angle. The angle ACB is 120 degrees. So the angle BCB is 30 degrees, which means that BDC is also an isosceles triangle. Let us denote AC as L, then CB is also L. Cos 30 is equal to L divided by AD, from which we get AD as equal to 1.155 L. Let us drop a perpendicular from D to CB. Since BBC is an isosceles triangle, such a perpendicular will bisect BC. Therefore, this distance is L by 2. We get cos 30 is equal to L by 2 divided by BD, from which we get BD is equal to 0.577 L. CD is also equal to 0.577 L. So now we have looked at the geometry of the truss. We next consider equilibrium of the truss as a whole. Let us consider moment about the point B. Then RA into AP is equal to 1000 into dB, which gives us RA. Now considering forces in the vertical direction, summation of forces on the truss as a whole must be 0, from which we'll get the value of Rp. We'll look at equilibrium of the joints A, D, and B in the next session. But here we discuss some preliminary issues. The circles here show that we'll consider the joint A, D, and B as free bodies. For each joint, we have two equations as earlier discussed. At A, we do not know the forces acting due to AC and AD, so we have two unknowns as well. So we will be able to solve for the two unknowns. In joint D, there are three unknowns. So we can't solve joint D first up. However, if we have solved joint A, then we know the force in AD, and as such in D there will now be two unknowns. So joint D can be solved after joint A has been solved. To start solving a joint, we consider all the forces to act out of the joint. So we consider that the force in AC acts out of A and the force in AD acts out of A again. If after solving the joint we get a negative value, then that would mean that the force acts towards the joint rather than out of the joint.